So, next we discuss problem number 4. It says the conductivity of a saturated solution of AgBr at 25 degrees Celsius is 8.5 times 10 raised to the minus 7 S centimeter inverse if the limiting molar conductivity of Ag plus and Br minus ions are 62 and 78 S centimeter square mole inverse. Then calculate the solubility product of AgBr. So, we can calculate lambda m naught of AgBr, right. Okay. So, lambda m naught of AgBr is lambda m naught Ag plus lambda m naught Br minus. This is according to Kohlraasch law. Okay. Now, we substitute the value of lambda m naught and lambda m naught of Ag plus and lambda m naught of Br minus. Okay. So, now you substitute the values. So, you get 62 plus 78 S centimeter square mole inverse, right. So, we get 140 S centimeter square mole inverse. Okay. So, this is the value of lambda m naught of AgBr. Now, for saturated solution, lambda m naught AgBr is kappa times 1000 by S, where S is the solubility. Okay. Okay. So, where S is the solubility. So, we can calculate S now. So, S is the solubility, where S is the solubility. So, we can calculate S. So, S is lambda m naught AgBr by this is kappa times 1000 by lambda m naught. So, kappa times 1000 by lambda m naught of AgBr. Now, we put the value. So, okay, so what is the value of kappa conductivity? Okay, so kappa conductivity is 8.5 times 10 to the minus 7 by lambda m naught we have calculated 140. So, here where kappa is the conductivity of the saturated solution of AgBr, and the value is given 8.5 times 10 raised to the minus 7 S centimeter inverse. So, we are putting this value of kappa here, and we can calculate now S. So, S will be 6.07 times 10 to the minus 6 moles liter inverse, right. Now, we got the solubility S. Okay. So, how we need to see how AgBr okay, so ionizes. Okay. So, AgBr ionizes as AgBr solid is in equilibrium with Ag plus Br minus. So, the solubility of Ag plus and Br minus are equal here. Okay. So, again you see the concentration of Ag plus equals to concentration of Br minus right here. So, since the solubility concentrations are the same, the solubility again is the same here. So, we can write, so Ksp, the solubility product of AgBr Ksp is concentration of Ag plus times concentration of Br minus, and as we said this is S times S, so we get value of S we calculated 6.07 times 10 to the minus 6 times 6.07 times 10 to the minus 6. So, we get the value of Ksp is 36.8 times 10 to the minus 12. So, this is the value of solubility product of AgBr. Now, we discuss problem number 5. It says the conductivity of a 0.01 molar solution of acetic acid at 298 K is 1.65 times 10 to the minus 4 S centimeter inverse. Calculate the molar conductivity, degree of dissociation and dissociation constant of acetic acid. So, the values of lambda naught of H plus is given as 349.1 S centimeter square mole inverse, and lambda naught of acetate ion CH3CO minus is also given 40.9 S centimeter square mole inverse. So, from there we can calculate lambda m naught of acetic acid. Okay. So, lambda naught of acetic acid we can calculate. So, lambda naught acetic acid. Okay, so we can write lambda naught acetic acid is lambda naught H plus lambda naught acetate ion, right, that we already discussed. So, now we put the values. So, lambda naught H plus is 349.1 and lambda naught acetate ion is 40.9. So, this is S centimeter raised to the 2 mole inverse. So, if we calculate this one, we get 390 is centimeters raised to the 2 mole inverse. So, lambda naught we got. Okay. Now, lambda c, so the conductivity is given. Okay. So, the conductivity of (0.01 m) solution of acetic acid value of kappa, right? So, kappa is given. Kappa is 1.65 times 10 to the 10 raised to the minus 4 S centimeter inverse. The value of kappa is given. So, we can and the concentration of acetic acid is also given. The concentration of acetic acid solution we call C, this is also given 0.01 molar. So, we can calculate lambda C is kappa times 1000 by C. So, value of kappa already given 1.65 times 10 raised to the minus 4 times 1000 by 0.01. So, if we calculate this one, we get 16.5 S centimeter square mole inverse. So, lambda C we have got and lambda naught also we have got. Okay, so, we can calculate degree of dissociation. Okay. So, the degree of dissociation of acetic acid if we call this one as alpha. So, we write this one as capital lambda here. So, lambda capital here. So, we call this is alpha. So, we write alpha is lambda c by lambda naught, right. So, lambda c value we calculated 16.5 is centimeter raised to the 2 mole inverse, and lambda naught value we calculated 390 is centimeter raised to the 2 mole inverse. So, if we calculate this one, we get alpha degree of dissociation of alpha is 0.01 0.0423. So, we got the value of degree of dissociation of acetic acid alpha, and we need to calculate dissociation constant also. Okay. So, acetic acid, again acetic acid dissociates as acetic acid is in equilibrium with CH3CO minus plus H plus, right. So, initially we had suppose C concentration C is the concentration of acetic acid, and this was 0, and at equilibrium concentration of acetic acid is 1 minus C times 1 minus alpha, this is C alpha, this is C alpha, right. So, where C is initial concentration of acetic acid, initial concentration of acetic acid. And here the value is also given, this is 0.01 molar. And alpha, as we discussed, alpha is the degree of dissociation of acetic acid, okay, that we also calculated. So, dissociation constant of acetic acid, the dissociation constant of acetic acid, because this is Ka, is concentration of CH3CO minus times concentration of H plus by concentration of acetic acid CH3COH. Now, concentration of acetate ion is C alpha. So, C alpha times C alpha by C 1 minus alpha. So, we get C alpha square is by 1 minus alpha. So, we can approximate this as C alpha square as 1 minus alpha equals to 1, we can consider because alpha is very small compared to 1. So, we can approximate 1 minus alpha is 1 only. So, value of C we know, C is 0.01 times alpha is also known 0.0423 raised to the 2. Right. So, if we calculate these two, okay, if we further simplify, so we get 1.8 times 10 to the minus 5. Approximately the value of dissociation constant of acetic acid Ka is 1.8 times 10 to the minus 5. Now, problem number 6 says the conductance of 0.0015 molar aqueous solution of a weak monobasic acid was determined by using a conductivity cell consisting of a platinized platinum electrode. The distance between the electrodes is 120 centimeter with an area of cross section is 1 centimeter raised to the 2. The conductance of the solution was found to be 5 times 10 to the minus 7. The pH of the solution is 4. Calculate the limiting molar conductivity of the solution. Okay, so, the given L is given, A is given, the length given, the length L is 120 centimeter. The area of cross section A is also given 1 centimeter square. Therefore, the cell constant L by A is 120 by 1, so we get 120 centimeter inverse. This is the value of cell constant, and the conductivity of the solution is also given. The conductivity of the solution kappa is 5 times 10 to the minus 7. Okay, this is also given. So we can calculate the conductance of the solution. Okay, no, not conductivity. Conductance of the solution is given. Okay, so the conductance of the solution G is given, not conductivity. The conductance of the solution. So this is not kappa. This is G is given. So we can calculate kappa. Okay, so kappa, the conductivity of the solution. Now we can calculate the conductivity of the solution kappa is G times L by A. Value of G is 5 times 10 to the minus 7 times 120. So if we calculate this one, we get the value of kappa. Kappa will be 6 times 10 to the minus 5 S centimeter inverse. Now lambda m we can calculate. Therefore, lambda m, molar conductivity, is kappa times 1000 by C, and C is also given. Okay, C is the concentration of the solution, where C is the concentration of the solution is given as 0.0015 m. So lambda m is 6 times 10 to the minus 5 times 1000 by 0.0015. So if we calculate this one, we get 40 S centimeter square raised to the 2 mole inverse. This is the value of lambda m. Achha. So another thing is given is pH. So if the pH is given, so we can calculate the concentration of H plus. Okay. So again, pH is pH of the solution is 4. Therefore, pH is minus log concentration of H plus. So 4 is minus log concentration of H plus. So we calculate, now we know what is the value of concentration of H plus is nothing but 1 times 10 to the minus 4 molar. So this is the concentration of H plus. Okay. Now this is a monobasic acid. So let us consider the monobasic acid is HA. Therefore, HA ionizes as, so HA is in equilibrium with H plus plus A minus, right. So initially the concentration of HA is C, this is concentration of H plus is 0 and concentration of A minus is also 0. At equilibrium, concentration of HA is C times 1 minus alpha, this is C alpha, this is C alpha. Concentration of A minus is also C alpha, where C is the initial concentration of the monobasic acid, HA, initial concentration of monobasic acid HA, and we know the initial concentration 0.0015, and alpha is degree of dissociation. Degree of dissociation of HA. So, we got the concentration of H plus at equilibrium. So, C alpha. So, C alpha is 1 times 10 to the minus 4, right, and value of C we know 0.0015. So, alpha is 1 times 10 to the minus 4 by C. So, you get alpha is 1 times 10 to the minus 4 by C is 0.0015. So, you get the value of alpha. So, alpha will be 1 by 15, right, alpha is 1 by 15. Okay, so, we need to calculate limiting molar conductivity. So, limiting molar conductivity lambda m naught, in order to calculate lambda m naught we need to calculate alpha, right. So, alpha we know. Okay, so, again alpha is, so alpha is lambda m by lambda m naught. So, lambda m naught we need to calculate. So, lambda m naught is lambda m by alpha. So, lambda m naught is 4 by 1 by 15. So, we get 4, no, this is 4 or 40 we got, yeah, we got 40, not 4, yeah, 40. So, 40 by 1 by 15. So, lambda m naught we get 600, okay, 600, or we can write lambda m naught is 6 times 10 raised to the 2 is centimeter raised to the 2 mole inverse. So, lambda m naught, lambda m we got, and then from pH we calculated concentration of H plus. So, from concentration of H plus, if we consider the dissociation, we calculated alpha. Once we get alpha, we use the expression alpha is lambda m by lambda m naught. From there we can calculate the limiting molar conductivity, or lambda m naught. Okay. Next is problem number 7. It says, in a simple electrochemical cell which is in standard state, the half cell reactions with their appropriate reduction potentials are lead 2 plus goes to lead with E naught value of minus 0.13 fold, and Ag plus goes to Ag with E naught value of plus 0.8 fold. What is the overall reaction of the cell, and calculate the EMF of the cell. Here we need to find out the reduction potential of the cell. So, here since the reduction potential of Ag plus Ag is more than that Pb2 plus Pb, therefore reduction will occur at silver electrode. So, the overall reaction can be written as overall cell reaction can be written as twice Ag plus Pb gives twice Ag plus Pb 2 plus. So, in anode actually oxidation takes place. So, in anode we get Ag plus goes to Ag, and cathode reduction takes place. So, lead goes to lead 2 plus. So, the half cell reactions, I can also write the half cell reactions, corresponding half cell reactions. Just to understand better manner, corresponding half cell reactions are at cathode. So, at cathode reduction takes place, okay, and at anode oxidation takes place. So, at cathode Ag plus goes to Ag, and at anode lead solid goes to Pb2 plus 2 electrons. So, we need to multiply this by 2. So, overall cell reaction, then if we add them we get the cell reaction. Okay. So, this is the overall cell reaction. Okay. So, in at anode oxidation takes place. So, lead goes to lead 2 plus, and at cathode oxidation at cathode reduction takes place. So, Ag plus goes to Ag. That is why the reduction will occur at silver electrode, Ag electrode. Okay. So, the cell reaction is written like this. Okay. So, the cell can be represented as the cell can be represented as Pb2 plus aqueous, and then Ag plus aqueous and Ag. Okay, this is the representation of the cell. Okay. Now, E naught cell is E naught cathode minus E naught anode. So, we write 0.80 for cathode, means for silver electrode, minus 0.13. So, we get 0.93 volt. So, this is the value of EMF of the cell. So, this E naught cell is the EMF of the cell, the standard EMF of the cell. Okay. So, in order to calculate standard EMF of the cell, we need to use the reduction potential of the cathode, E naught cathode minus E naught anode, okay, reduction potential of the anode, and the value we get is 0.93 volt. Next, we move to problem number 8. It says zinc rod is dipped in 0.5 molar solution of zinc sulphate. The salt is 95% dissociated at this dilution at 298 K, calculate the electrode potential given that E naught value is given, zinc 2 plus 2 zinc is minus 0.76. So, the electrode reaction can be represented as we have zinc 2 plus and then plus 2 electrons gives Zn solid. Okay. So, according to Nernst equation, at 298 K temperature, E Zn 2 plus 2 Zn is E naught Zn 2 plus 2 Zn minus 0.059 by n. N is 2 here, number of electrons. So, log concentration of Zn by concentration of Zn2 plus. So, value of E naught is given minus 0.76 volt, minus 0.059 by n is 2 here, log concentration of Zn solid is again 1. So, 1 by, now 95% dissociated. So, 0.1 molar we have solution. So, 95% dissociated. So, we get 0.095 molar, right. Okay, so, concentration of Zn2 plus is 0.1 molar times 95% dissociated. So, we get 0.095 molar. Right. That is how we can calculate the concentration of Zn2 plus. Okay. So, if we calculate this one, we get the value of E Zn2 plus to Zn. So, the value of E Zn2 plus to Zn is minus 0.76, and if we calculate this quantity we get minus 0.03. So, we get E Zn2 plus to Zn is minus 0.79 volt.